All right. Hello, everybody. I'm Alan Geister, and this is my matrix operation project. All right, so I'm going to begin by presenting my pseudocode, and yeah. So, input correction function. So this is kind of the beginning of my pseudocode, and I declare my global variables. I kind of have to declare I, J, and K here, mainly because in dev C++, which is my primary compiler, it doesn't like it when I, in loops, define it inside the loop and then redefine it. It's a bit odd, but it's an older compiler, so that's why. But the reason why I use this input correction function for whenever, or to call it whenever there's a user error for cases of the addition and subtraction or the multiplication option is because these the lines of code are pretty much identical between both cases. And yes, I did account for like slight printing differences for each case. But yeah, basically it'll just print every new line. And the reason why there's not a slash n here is mainly because when you use the get user input, so what that looks like in like C is scanf primarily, and when that happens, it just starts it on a new line anyways. Oh wait, no, here it'll be next to the line, but if I did a slash in, it would be the next line over. But anyway, so that's the input correction function. Simple, just some prints and scanfs, not too complicated. This is my get determinant function used to calculate the determinant whenever called. So for all intents and purposes, every matrix, the first index is going to be treated as the row, and the second index is going to be treated as the column. Obviously, theory 3 gives like the maximum number of values in each um, array. However, it'll start from 0 to 2, so 0. So this one would be the top left value on a 3 by 3 matrix times um, I don't have the thing right in front of me, but to remember it, it'll be the top left times the quantity of the middle value times the corner value minus the or bottom right corner value minus uh, the value right underneath the middle value. Like when I say middle, I mean like straight middle, unless I specify it's at the top or the bottom, times the middle right column or third column, middle column, plus the top middle column, um, first row, zeroth row, first column, times the quantity. This would be this would be first row from starting from 0 on the middle of the left column times the oh, I forgot a subtraction here. There's supposed to be a little subtraction symbol here. One second, let me just add that here. Anyway, so the this value times the bottom right corner minus the bottom left corner times the middle right corner, and then that's going to be I have another error. There's supposed to be an addition sign here, and then plus the third column value on the top third column value or the value on the top right times the quantity the first value wait, first value on the second row or the middle of the left column times the um, bottom middle minus the this would be the bottom left value times the middle value, absolute middle value. And then after that, after it calculates the determinant for whatever matrix you input here, it has to be primarily 3 by 3 matrix because that's what we use in the determinant function later on. It'll return it, and whatever variable I set it as, it'll be this value. So the first function I define, just to make things simpler or use less lines, is a operation function. So it'll take in the row and the column of the first matrix, the row and the column of the second matrix, and it'll take, these will be in the actual main, these will be inputted as um, matrix A and matrix B, and then operation, it's the type of operation. So they'll just be a single char, but for the sake of readability, I put them as full words. In the actual code, it'll be like if operation equals A or S. But for operation, I'm having addition subtraction be kind of under the character A because later on you'll see I set in the conditional um, for the addition section which one? Oh yeah, right. Where is it? Oh wait, I'm a fool. You'll see it in the get matrices function later on. But anyway, we'll go through this. But yeah, so this will iterate through the first. So how majority of these loops will work is, except for the transpose loop, it'll go between from 0 to 2, because if, for example, if you enter 3 here, it'll be from 0 to 2. This will iterate through each column in the first row, then it'll go to the next iteration, each column in that row, and then the next iteration, and so on and so forth. And if the matrix operation is subtraction, which will begin from the operation, then it'll subtract matrix 2 from matrix 1, else it will add automatically. Then these spaces are just for matrices format. Then as for the multiplication, it'll be 3 because, as we'll see in the next slide, this is the formula for each element in the matrix. So what it does, it'll take the um, first element on the row times the first element on the next column times the second element in that row times the second element of that column, and then it'll keep doing that for each element, and it'll be added. So you define a sum, add it to the sum, set it equal to the sum. It'll after each iteration for the column loop, each iteration it'll reset the sum so that it doesn't, so that each element's calculation doesn't bleed in or into the next element, and then as a result it'll print it and display it for the user. Then as for the operation transpose, simple function where you define your rows or the column value that is defined by the user, and then the row value becomes the column value. Same logic for the loops as I explained earlier, except here, the reason why you put j here is because this is supposed to be the column number, and this is supposed to be the row number. So it'll iterate from each column, like each column value from the matrix becomes a row value, and then vice versa. Every like row value from the first matrix or whatever matrix you enter into the function becomes a column value. So row to column, column to row. And that's accounted by this equals. And then that loop ends. And then I have code here to display it, similarly to previous code, where it just prints the result. And then the final part in the operation function is the case where, oh yeah, this is all in one. There's 4 conditions. If it's addition, if it's addition slash subtraction, if it's multiplication, which was this one, if it's transpose. But this part starts the solving equations with, oh, there's a little mistake here. Solving equations with um, Cramer's rule. And the reason why we have the determined function first defined in the last couple slides is so that we can call it here, because C is a bit picky with its order. Then first condition it checks is if it is 0, the system of equations is unsolvable. It'll return 0, and since this will be called in the main function, where the function of main will be defined as an integer, it'll stop the entire function immediately. And this just ends the if. However, a counter argument made here, instead of setting this is equal to this, either it should be is less than or equal to a tolerance value really close to 0 to account for um, just numerical limitations and how the compiler reads the number, which is understandable. However, I found after playtesting with this, it typically can solve most things anyways. Although in the actual code, if I want to test it more regularly, I might change this to if determinant is less than or equal to some really small number, like for example, 1 times 10 to the negative 4, something like that. If I want it to be a bit more less susceptible to breaking. And here declares the matrices, because in Cramer's rule, you go through each matrix and you replace the X column with the B matrix or your solution matrix, and then for you to get your Y, you do it with Y, where you replace the Y column with your solution matrix. Same with Z. You calculate all these determinants, and then you divide by the main determinant, which was in the previous slide, this one. This would be the denominator determinant of the equation. And then, so this one iterates um, again from each column, then goes to each row, and then here it's checking if the column number isn't the X column, which would be the 0th index. It'll set it equal to um, the matrix A, because this will be matrix A when this function gets called later, or like the initial set of equations. It'll be set to that element number. Else, it'll be set to the solution matrix here. And then similar logic for the Y column, except with the index condition being 1, or the Y column. Then if not the Y column, it becomes the equation matrix value. Else it becomes the solution matrix value. And loop. Same here, except again with the Z column, where if j is not 2, the Z column, it'll set it to the um, equation matrix, and then else it'll set it to else being if the column is Z, it'll set it to the solution elements or solution matrix. Anyways, declare then this then we call the getDeterminant function, where we enter the matrix into the determinant function, and then it'll spit out the determinant of the function. So here, matrix X, it'll get the determinant of X matrix. Here, determinant of Y matrix, determinant of Z matrix, and then I calculate the X value of the determinants by dividing each X, Y, and Z determinant by the matrix equation determinant, and then I print the answers to display them. Now this is the gate matrices function. So I try in this entire function to have the format be built for each case. So the very first thing that gets called is if the operation is not transpose and not equations, it'll print out this as if it's asking for a matrix A. In this one, where it's addition, wait, it's not if operation if operation, I'll say if operation is addition, subtraction. Wait, this is supposed to be, I was silly here. If operation is transpose, it should just go straight to this. Then, oh yeah, if it's a transpose, it should go. So this, if it's a transpose, it'll ask you for just a single matrix, because it's a little weird to ask for matrix A when we're not going to have matrix B. So I counted for this little prompting miscommunication. I mean, it's not too big of a deal, but I added it in anyways. Here, it just checks if it's like addition, subtraction, or multiplication, in which it'll do this. And then the reason why we don't include equations in here is because it's a 3x3 matrix equation, so you don't need to ask this. Similarly with the and then if the matrix is this condition accounts for if the operation is the equation solving the system of equations, where it'll set the A row, A column, and B row stuff to 3 and B column to 1, because you only have one column in the B solution matrix, and then obviously you have 3 in the rest. and then it'll end the if, and then this condition checks if it's not transposing out equations, because again, for equations, you don't need to ask this. It's 3 by 1. And then for this part, not transpose, you don't have matrix B when you're transposing only one matrix. And else, it'll set your B row and B column to 0. Wait. This is necessary for the transpose function. However, for the equations function, if it is equations, it'll set to, let's see, small little error here, else if operation is transpose, there we go, small little error there. It's supposed to be, this only occurs for transpose due to how I've designed the transpose conditional, because if we go all the way back to here, if operation is transpose, oh wait, no, it's just initializing them. So this is just, these are just zeros because I originally was going to use these as conditions for determining if it's transpose, but this isn't necessary. But I still have to initialize them because they're global variables. But anyway, get matrix C functions. This one, if this one checks if it's addition subtraction based off the operation entered into when it gets called. And then this one, this is the fail condition for addition and subtraction, where if they're not square matrices, this is what the while loop, this will only ever run if the condition is not met. So if the user keeps inputting the wrong error, it'll keep running, and then every time it does that, the get inputs correction gets called, where it just basically reprompts the user. You saw it earlier. This one is the multiplication condition, where it's checking the column number of A and the row number of B, checking if they're equal. If they're not, then you can't multiply. And then if operation is transpose, then this is basically, oh yeah, all of them just check if it's a positive integer or positive, well, not integer, but positive value. Because if it's not, you can't really have a matrix with 0 columns or 0 or negative columns, that sort of thing. And this one is special for transpose because you're only checking one matrix, so you would only need to reprompt the user twice instead of 4 times. And then this one declares the matrix A, matrix B, and then this checks if it's transposed, because if it's transposed, then it should only ever say like, please type in row, please type in, yeah, the column, no, not row number, row element. I mean, number does work, but I think it's more specifically better for element. Then it gets the user input for the float for that specific element. So first iteration will go 0, 0, second iteration will go 0, 1, 0, 2, and then it'll only go like 0 to a column minus 1. So for a 3 by 3, it would be 0 to 2, for example, and then it'll go to the next I iteration to the next row, and you get the point. Same lot, and then that's if it's transpose. For every other case, it'll just ask you to enter it in for matrix A, because in every other case you have two matrices, so it makes sense to have the A there. And it ends the loop. If this condition is checking if it needs to ask for matrix B in this format, because for transpose, obviously you don't have a matrix B. In equations, you don't need the column number here, so it only makes sense to have the row. So that's what this is checking for. And then in the case of you're solving for equations, it does it where it's just asking for the, can I not change it? Please type in, wait, what? Please type in row. It should just be, oops. This should just be, please type in row number for matrix B, because you only have one column number. There you go. That was weird. I swear I changed this, but I guess it didn't. Okay. And that's just for the row. transpose matrix B from 0 to become. Become is just, oh yeah, I guess here, because it's defined as 1, 0, this will only run once. But, oh wait, no, I don't need to put this loop here. This loop does not need to exist. I did change it, I don't know why this version's a bit odd, but whatever. Please type in row number for matrix B, and this should just be 0. I know this is pseudocode, so the typing doesn't matter, but for me it just helps it readable. Yeah, the reason why it's 0 here is because it's only one column, so user float, and it just sets this as the column. Should be, yeah, okay, that's correct. Okay. And if operation is transpose, this condition just checks whether it should print it out in with the specifying matrix A or not. If it's transpose, you don't need to specify. If it isn't transpose, then it'll be matrix A. Then here it'll just display. Oh wait, it should be capitalized. It'll just display the matrix. And then here, if operation is not transpose, here is matrix B. Basically, if it's not transpose, you'll print matrix B anyways. And this will always run till this works for both equation cases and addition, subtraction, multiplication cases. It does that because this gets accounted for in the case that it's just because it'll run only once. And then J will be set to 0, so this would still work. This is important to keep. The reason why we can delete it here is because we can just hard set it to 0. Here we can't, because this operation accounts for every case. Yeah, anyway. Then this last operation, if it's for specifically addition subtraction, it'll reprompt the user to add or subtract. And then based off that input, if input is A or B, A or S, because the tract is A. If input is A or S, basically attraction or subtraction input, the operation will be the input, and if we go back to the function, for the operations function, you'll see it checks it, so it'll be, I guess, because it'll be ARS in the actual code, but for simplicity's sake and subtraction, it'll be a single card, it'll just be ARS in the actual code, but for better readability as a pseudocode, the whole point of pseudocode is to be easy to read, so yeah. And then else, because of my previous else if statements, this should account for the multiplication and transpose case. Wait, it should just be else, because all the conditions are the same and accounted for in my get matrices. No, made in my matrix operations because of the conditions here. Yeah, it's accounted for here at the operation, and then obviously the values get accounted for. So that's the get matrices function. Here's main, where basically after you're just calling them for each input, so it'll prompt the user with a choice. These 4 choices get character on the following: addition, subtraction, multiplication, transpose, find solutions. It'll get the user input. This just checks if the user inputted something that makes sense. It is going to be based off caps lock, so it should be lowercase. And then this if else chain just checks if input is A, addition, subtraction, it'll get matrices, addition, subtraction. In the actual code, this will be like the character A, and then because the input is accounted for here, right here, because the operation here is input, instead of the argument of the entire function, it'll be this value. So that's how that works. And then for these, it's accounted for. And then that's the entirety of the main function. Now, this is my human code. I entered the prompt into Gemini, and this is what Gemini gave me. So it starts off the function by defining a get matrix input, where it has the matrix, the rows, the columns, enter number of rows, read rows, enter number of columns, read columns, read being in this case the user, from I to 1 rows, enter element, for I from 1 to rows. This isn't accounting for the indexing start, so this is starting assuming from 1 to number of rows. So this one's here, the AI considers it to be starting from 1 instead of 0. I guess that would make better sense for readability, because I guess most non-programmers would understand, oh, how do you start from 0 instead of 1? Because you don't count like that. That's just how the AI is function. Then after that, it will return the matrix. It'll return the matrix. Then here, this is displaying it. So I assume when you enter the matrix here, it'll just print like each element. And then obviously with the bars, here it actually separates the add and subtract functions into different matrices. And then here it's basically similarly to what my code, it equals, it's just it's almost the exact same for both of these, except instead of having the add and subtract be in one function and be accounted for by the operation as an argument, it uses the matrices and the rows as variables. I assume here when it says rows columns, it'll in the actual pseudocode or in the actual code, it'll be row 1, row 2, column 1, column 2. This is more general notation, although I think it's a bit more confusing for like a non-programmer. Um, then it specifies here. Ah, yeah, I forgot rows B. Oh, this is why you check AI and you don't follow it blindly. Rows A, rows B from 1 to cos B. This one is the multiplication value, matrix multiplication, where it'll, so again, similarly to mine, it'll iterate and reset the sum. And then here, first element, first element row 1, first element column 1, first second element row 2, second element column 2, same column, same function as line effectively, and then it'll return the matrix. Transpose, again, very similar, just swap, does rows, then columns, and then defines it as columns and rows. Very similar. Calculate determinant, term 1, term 2. Okay, it splits it off into, instead of putting it all in one equation, it separates it into variables. I assume these would be floats. And then adds, subtracts the y column because it's just how J is defined. So matrix as a third column, it's a third cofactor matrix. I believe the proper term is cofactor because top third column's cofactor, second column's cofactor, and then first column's cofactor. Anyways, same way to do it as mine, except done a little bit differently, where it defines the variables, then uses them in the final determinant, then returns them. And then as for this, it had solving solving system of equations all in one function. The issue I have with this, it's effectively the same as mine, except you wouldn't need to oh wait, it only takes matrix A result vector. Dx to solution vector. How does it determine matrix A? Did this forget to? Okay, result vector is this. Okay, so this is just a fancy name for the solution vector. Okay, I see. Then, yeah, okay. And then it defines, okay, so this is our matrix B. This is the solution. Determinant D, call 3 by 3. This one calculates the determinant of the first of the equation matrix, close to 0. Okay, like I said earlier, if I needed to change it for the program to be more robust and work in better cases, close to 0, I think I would use a tolerance of like less than or equal to 10 to the minus 4. And then here, it's effectively the same. Dx matrix equals A. Wait, what's this first? Dx matrix A. Oh, it sets it as. Okay, so this is this is different. So instead of making a new matrix and then like iterating based off the condition of the column, he defines it. The AI defines it as the determinant matrix is the same, except it replaces the value in a separate loop. That is more efficient, I will admit, than what I thought of. And then it calculates the determinant right after the loop instead of me doing it all at the end. Okay, and then it does it for determinant y, and then determinant z, calculate solutions for Cramer's rule, then just x over determinant, primary determinant, y over primary determinant, z over primary, and then returns the solution vector. Okay. And this is where the AI takes a completely different turn where it'll handle the addition and subtraction in a separate function. So it has multiple, it splits, it's like if my code was divided into even more functions. But anyway, oh yeah, I forgot to be using the slice row. But handle declares, instead of me having them be global variables, here he defines them as local variables, and then it'll prompt the user to get matrices for A and B using the get matrices function. This is its failure condition, checking for square matrix. Although here it actually doesn't check if the user's input is an actual makes sense. So here if you put in negative values, so this is wrong, or not wrong, but partially wrong. Then A or S, like I said earlier, option A, B. Oh, okay then. So here's an if statement conditional for addition subtraction. And then else, invalid operation choice. Oh, it prompts the user if it's okay before going into the actual displaying of it. Okay. And here it will display the matrix for the addition, subtraction, after calculating the addition or subtraction. And then, oh, if they chose wrong, if they made a different value here, okay, that makes sense. Okay. Understood. Then we have the handle multiplication function, declares them locally, calls them again. Yeah, okay. They're repeating this line of code in each function, which is why I didn't want to separate them into separate functions. This is inefficient. Failure condition also doesn't check if the column or row values are logical, or not even logical, are like positive integers. Doesn't even check it. Then gets the return matrix. Wait, result matrix calls it. Oh, it's calling the matrix multiplication function. Then it prints the result, calls the display matrix. This one actually is the thing that displays it. This is just the prompt beforehand, hence function. Handle transpose, similar logic, declares it locally, calls the get matrix function. Result matrix is the matrix transpose function. Print statement before actual printing it, or like saying, hey, I'm about to print this. Call display matrix, which actually displays the results, and function. Then this one's where it gets a little bit more complicated because it defines it. Again, it wouldn't need to redefine everything if it uses global variables and then accounts for it in an operation function. This is inefficient. From 1 to R, from row, enters for enter value for matrix A, enter for matrix B. Solution vector calls the solution linear equation function. If solution vector is not null, then assume it's because it can be a non-real value. Wait, what's the point of this value? Can just print it directly because it doesn't have an else if. Again, the AI is lacking an else if function here, so that's missing because what if it is null? what will it display for the user to read. Then here's the main structure of the code, main function, where it'll basically just call based off the user's action. It'll call case 1, it'll call the handle addition subtraction. For case 2, handle multiplication. Case 3, handle transpose. Case 4, handle linear equations. And for whatever reason, the AI wanted to add an exit choice for some reason. And instead of using characters, the options are 1 to 5. That's okay. And then end switch. Oh yeah, another difference between my code and the AI code is Gemini used a switch case. I use just regular if and else. I find that to be, for me, that works better, but here it doesn't really matter. And as you can see, based off the actual code, the AI is actually lacking a couple of things. Like it's lacking more robust fail conditions. I mean, yes, for the resultant stuff where it's checking if the determinant is 0, that's a bit more robust than mine, but I even pointed that out. Other than that, I find the fact that it separates everything into so many different functions to be a little bit counterintuitive, because it has so many functions, but you wouldn't need to recall um, asking the user to re-input a value when it's the same syntax for addition, subtraction. Like these these are mostly the same function, except this did not need to be multiple functions. You could have just had an if conditional for this. They did not need, oh wait, no, this is the handling. I meant specifically addition, subtraction, right? Yeah, these did not need to be different functions. And then handling them can all be one function, because there's a lot of code that's very similar between all of these, which is why I chose to do what I did. So in general, I think um, I think for the final project, I will be using my pseudocode instead of the AI's, because I find it to be a bit lacking in many regards. And anyways, that's my pseudocode for my matrix operation project. And thank you for watching.